Okay, so the topic for today is going to be depth first search, which hopefully most of you are familiar with and have seen. But what I would like to do is to give you a very formal treatment of depth first search to demonstrate the kinds of things that can be done with DFS. So let me go ahead and start writing. All right. Okay, so sorry, one second. So remember, depth first search depth first search, arguably is an even simpler algorithm than breadth first search. So the way the depth first search works, and it'd be useful for us to think of the graph being directed, because many of the interesting applications of depth first search are for directed graphs. So let's say you visit a vertex, then you take a neighbor, you visit that neighbor, you go to a neighbor, you visit the neighbor, and you keep doing this until at some point you hit a vertex, all of whose neighbors are visited, and then you backtrack, and then you go somewhere else, you visit everything, so on and so forth. So it's basically just a standard process of backtracking in a graph. And let me write out a very simplified depth first search sort of code, and then I will write a more detailed one. So when you do depth first search of S, you visit the vertex S, and then you say for every, let's say, U in the neighborhood. Now I'm going to say N plus because that is the out neighborhood. Okay, so for every vertex in the out neighborhood that is not visited, for every vertex that is not visited in the out neighborhood, what you would do is you would call DFS of U. Right, so it's very cleanly written as a recursion. Okay, so this is sort of your prototype code for DFS. Now, if you think of what breadth first search maintained, breadth first search maintained a predecessor and a visited array, which essentially gave distances. In depth first search, there's going to be the notion of time. So you should think of a clock ticking at each operation, or at each visit, technically. So technically we'll think of like int time being a global variable. And what we will keep track of are two arrays that I will call disk, which is the discovery time. This is going to be an array indexed by the vertex set. And I'll have another array called fin, which is the finish time, and which is also an array indexed by the. Now that I have these global data structures, let me give you sort of a code for DFS. So the first step is, we'll say that visited of S is true. Second step is to say that the discovery of S is the current time, and then we will increment the time. Right? So this is the clock ticking. At every time there is a visit, the clock ticks. And actually we'll see that every time there is also an exit, the clock will tick. Okay, now is our main loop. So for all vertices in the neighborhood of S, and I'm going to say n plus, remember, because this is the out neighborhood. For all vertices, if visited of u is false, right? So the vertex has not been visited, then we do our usual. We'll set the predecessor. So we still maintain a predecessor and a visited array, right? We also, just to be clear, we also have a predecessor and visited as before, right? As in BFS. So we set the predecessor of u to be S, and then we do a recursive call for DFS of u. Finally, sorry, just let me reorient things a bit. Finally, after the loop finishes, we set the finish time of S to be the current time. Note that the time will change in the recursive calls. Time is a global variable, right? This is a global variable time, and it will change in each of these recursive calls. So the finish time is not going to be the same as, whatever, the discovery time plus 1. It's going to be something potentially larger. And of course, after this, after the finish, we'll do another time increment. This is your code for depth first search. Are there any questions about this? Does the time concept make sense? There's basically a clock ticking, and every time a recursive call is made, you store the time that vertex was visited or discovered.
So when the algorithm is complete, doesn't that mean earlier nodes will have a larger time than later nodes?
Yes, that's exactly right. Nodes that were called earlier will have a smaller discovery time than further nodes.
Sorry, the finish time.
Sorry, I didn't get that. One at a time, please.
The finish time. So earlier nodes would have a larger finish time, right?
That's okay. So yes and no. I will show you examples where that is not necessarily the case. Note that this graph is undirected. The graph could be directed. So for example, okay. So first I need to hold that thought. Ask me again in a couple of minutes.
Okay.
Somebody else had a question.
What's the reason to increment the time after setting the finish time?
I just think that for our arguments, it'll be convenient if all finish times and discovery times are unique.
Unique, okay.
Right.
Sounds
so
good.
that way, we don't. I don't think it'll affect things, but there may be certain corner cases where it's easier to argue when things are unique.
Okay.
Anybody else? Any other questions? Okay, so just to have everything in front of us, let me write out what is DFS on the whole graph. So we initialize all the arrays. These are the global data structures. We set time to be 0. And then we do what we normally do for BFS. We'll say for all vertices, if...
Can you move the paper?
Oh, yes, sorry. If visited S is false, then we call DFS on S. And just like DFS. And so what is the output? The output is the DFS forest as given by the predecessor array. And we have the discovery and the finish times. This is the output. So unlike DFS, where the output is essentially just the forest, and you can read off the shortest path distances from the forest, in DFS, we have the discovery and finish times. Okay? So, now let me ask you a few questions. And I want to, I'll poll you to see if you get the answer. So my first question is, suppose DFS U is a recursive call made in DFS S. Is the discovery of U less than the discovery time of S? A is yes, B is no. I'm going to launch the poll. I will also show you sorry, let me see if I can get everything into the screen. There you go. Right, so you have the okay, so there is, there seems to be like a 1/3, 2/3 split in this answer. Okay, so the answer is no. Why?
Because time gets incremented before DFSU is called. So by the time we enter DFSU, the time having been incremented is now greater than DFSS.
Exactly, right? So you should think of the timestamp as basically like the clock keeping track of the algorithm. The discovery time is basically the time that DFSS is called, right? When DFSS is called, you set visited to be true and you set the discovery time to be the time. So if DFSU is a recursive call made, that means that DFSS was already called, which means the time was already set and the time got incremented. Exactly as you said, exactly as the answer said. So the discovery time of U is going to be greater than the discovery time of S. So if you think of this as time, here is time. Let's say this is the point that S was discovered. That means DFS of S was called here. Any recursive call made has to be afterwards. And so that would mean that the discovery of U was later. Okay, just to sort of complete just to complete this, again, suppose the same setting. So suppose DFS is a recursive call made, is the finish time of U less than the finish time of S? A is yes, B is no, and C is maybe or maybe not. So what I mean by C is that, this may happen or it might not happen, right? So you're saying that it could be or it may be the case, or it might not be the case. And let me launch the poll again. Again, it's the same setting as before. So, sorry, let me show you the code for DFS of S. There you go. Okay, so I'm actually not going to give the answer. Instead, I'm going to say something, and then I'm going to relaunch the poll. So at this point, it's sort of 60-40. 60% of you got it correct, 40% of you have it wrong. So I want to give you a hint, and then I will relaunch the poll. So what is the hint? Well, I'm just going to draw something here. So suppose you have a procedure A, making a recursive call to procedure B. Think about which process or procedure finishes first, A or B. So just think about that. Procedure A makes a recursive call to procedure B. Which procedure finishes first? Is it A or B? And if you think about that and you understand what that question means, you will see the answer to my second question. So I'm going to relaunch the poll for the second question. Is this finish time of U less than finish time of S? Okay, so it seems that there's more of you have come to the correct answer. And yes, the answer is yes. Why? Because in this question, if procedure A makes a recursive call to procedure B, then who finishes first? B has to finish first Because it's only when B finishes that A can finish. A made a recursive call. So if B doesn't finish, then A has not yet finished. And it's the same argument here. DFSU is a recursive call made in DFS of S. So if DFSU has not finished, then obviously DFS of S cannot finish. Right? If you look at the code over here, DFSU has to finish first before DFS S can finish. Okay? So
I thought I didn't see the suppose as a recursive call. So I thought maybe S doesn't have any neighbors. And so
this was under this assumption. Suppose DFSU is a recursive call, then these two questions.
So we are assuming that for this question, we were assuming that S always has some directed neighbors.
No, it's not necessarily. I'm just saying it's a recursive call made. But yeah, you assume it has neighbors, but it's a recursive call made.
Okay.
Okay. Now I'm going to state a theorem here. And indeed, I'm going to make this an exercise. But please ask me questions about whether this makes sense or not. So I'm going to just state this as a claim. This is a useful claim. And I will say the vertex, let's say, I'm going to call it X and Y just to distinguish between these. The vertex Y is a descendant of, well, okay, let me use U and V. The vertex V is a descendant of vertex U in the DFS forest if and only if the discovery of U is less than the discovery of V, and the finish time of U is greater than the finish time of V. So sorry, I'm going to make the statement. Let me come back to it in a moment. Okay, let me come back to it in a moment. Let me ask you another question. I'm going to ask you another question. And I want you to, this is like a fresh question. So U and V are new vertices. Suppose discovery of U is less than discovery of V. Then finish of U is greater than the finish time of V. True or false? Ignore what I've written before. Ignore that. True or false?
Professor,
yes?
for this, which one is the descendant then?
I haven't said anything. I have not said who's a descendant or anything. I just said, suppose the discovery time of U is less than the discovery time of V.
Okay.
Okay, so it's roughly 50-50. Can someone justify their answer?
I guess I can. So I was going with true.
With true, okay.
Yeah, because if the discovery time of U is less than the discovery time of V, it means that U is discovered first,
Yes.
and so V is the kind of the descendant of U. But then like the finish time of U is greater than V, because since V was discovered afterwards, so the recursive call of V would then finish quickly as
Okay.
compared to the finish time of U, and so that is where the statement holds.
Okay. All right. Does someone who said, so you said it was true, someone who said false?
I said it was false.
Why?
And I think it's false because V might not be a descendant of U.
Right. So can you give an example?
So if you have a graph where if you just have like a triangle, for example, and you
Okay.
start at or not even a triangle, like just like a little like L-shaped graph,
Like that?
and you start at the like right angle.
Right there. Okay. So I'm going to call that U.
Yeah.
All right.
Then I guess. Oh wait, no.
Sorry.
Go
I
on.
guess you want to say U and V are both descendants of one another node.
Okay.
Then you
all
will
right.
know the discovery time U is smaller than discovery time V. And we will have last finish time of U and
Something like that.
in this case we will finish the V first.
Or you could finish
Okay.
U first, right? You could
Okay,
discover
we will-
U first,
yeah.
but you'll
Yeah.
also finish it first.
Yeah. First we will discover the U and finish the U.
Exactly.
Yeah, and then the finish time of U is smaller than the finish time of V.
Exactly.
Yeah.
So you don't even need the direction. This example is enough. But if you make it directed, it's even more easy. I can give you a simple directed example. Suppose this was your graph. This is it. Except this is V and this is U. Now remember, when you call DFS on the original graph, you basically loop over all the vertices. So your loop might have started at U. So you would discover U and you would just finish U immediately. Then you would discover V and then finish V. Does this make sense? Therefore, the statement is false. It is not necessarily true. Someone pointed out an argument which was the argument that it was true is only true if it's a descendant. And indeed, the claim is the vertex V is a descendant of U if and only if these conditions hold. Is this making sense? So please ask me questions if this is not. Because this is really key to understanding the power of DFS. So is this clear? A is yes, this is clear. B is no, it is not.
Professor, I think I mean, to me, it's clear I answered false, but I think it would be better if I know that the finish of U is, I mean, it's a descendant of V, then that would be definitely the answer is true.
Yes, that is what this claim says.
Okay.
That's exactly, you're right. If V is a descendant of U, then definitely this is true. This is in some sense, okay, I'm going to say, quote unquote obvious, but it's not obvious. But if you think about it, when V is a descendant of U, that means that DFS of V is a recursive call made within the recursion stack of DFSU. Like DFSU makes a recursive call, which makes a further recursive call, so on and so forth, right? So that means DFS of V, that procedure was a recursive call made. And because it's a recursive call made, these conditions hold.
Okay. Mm-hmm.
Okay, good. I think most of you are following. So for the person who had answered this is true, there was someone who gave an explanation. Does this make sense to you now? Do you see why it's actually false? But what your argument was correct in the case it's a descendant.
Yeah, I got it.
Yeah? Okay, good. All right. So hopefully now that you see these things, I'm going to state a theorem. Which is incredibly useful when understanding DFS. And this is called the parentheses theorem of DFS. It's really, the best way to show it is a picture, and then I will write it down. What it says is, if you look at the finished discovery, so if you think of discovery as an open parentheses and a finish as the closed parentheses, then it says the discovery and finish times give a valid parenthetical statement. What this means is if you think of the discovery of U as something like that, and the discovery of V as another parentheses, then if you look at the corresponding finish times, the open and the closing have to form a valid parenthetical statement, which means this cannot happen. So it either has to look like this, or it has to look like this. In this case, so this is U. In the former case, V is a descendant of
Professor,
U.
can you show the graph diagrams of these parentheses that will like help clarify?
The graph diagrams, I'm not sure I know what you mean.
Like how like when you discovered U and then V's, and then like for the left one and for the right one.
You mean you want to see examples of these?
Yeah, just a short graph.
Sure. I will show an example of these. Sure, I will. Let me first write down the statement completely, and then I will show you examples. Any questions about this? Okay, good. So let me just write this down formally so that you have a formal statement, although the statement is going to be identical to this. This is just saying for all vertices U and V, if the discovery of U is less than the discovery of V, right? Then either case 1 happens, which is this setting here, which would be that the finish of V is less than the finish of U, and V is a descendant of U in the DFS forest. Or, so this would be, or the discovery of V is greater than the finish of U. And neither vertex is a descendant of the other. Okay, so this is sort of the formal statement here. It's written as the parentheses theorem because you can interpret as a parenthetical statement. You can also rewrite this in terms of a parenthetical statement, but I think that this is just the more succinct way of writing down this condition. Are there any questions about this? I will give you examples. I will show you concrete examples where one happens and the other doesn't, or where one happens and then the other case does. But please, any questions about the statement itself?
Yeah, Professor, just one question. Does it matter if the graph is directed or undirected in
For the
all
statement?
of this discussion?
No.
Really, for all the discussion that we're having?
No. All the statements I'm making are equally valid for directed and undirected graphs.
Okay, so just one follow-up question then. Can you please bring up the last paper where we had just two,
This example, so in this example, the argument I made is only valid when it's directed, but you can also look at this example.
Right, okay. So in the last case, I just had a question, like if we started with U, we would not visit V, right? Or am I understanding this wrong?
You're absolutely right. If you started DFS on U, you would not visit V.
So if there are no outgoing edges, in a directed graph, if there are no outgoing edges, then we would essentially not visit all the vertices, right?
Yeah, but you look at what DFS on the entire graph does is it loops over all vertices.
Oh, okay. Yeah, that makes sense. Okay.
Right? So I want you to think of DFS being run on the whole graph, where you started off with U as a source, and then you will start with V as a source.
So we have a way of traversing over. The graph knows all the vertices. So
the graph knows exactly. Yeah. You have to traverse the whole graph. Exactly. So in the end, all vertices are visited.
Got it. Yeah, that was my only question. Thank you so much.
Okay. And actually so for the purposes of understanding a lot of this, it's useful to keep directed graphs in mind, because those are some of the most key applications. But now let me just give you examples of both of these, and then we can discuss the proof of the statement, which indeed, once you start writing down the arguments, it should be apparent what is happening. Okay. So just to give examples for actually any questions about the statement? Okay. So let's go back to this graph here, this simple example. It's a very nice example provided. And let's just say that suppose DFS started at S. Okay, let me now draw out the timeline. So what's going to happen first is you have S being discovered. So S is going to be, this is the discovery of S. Now at this point, it's going to choose between the neighbors, right? Because it has to visit one of the neighbors. So let's say it visits U first. So this will be the discovery of U. Now U doesn't have any unvisited neighbors, so U is going to immediately terminate, and this is going to be the finish of U. Right? So then it goes back. So why does it go back? Because let's look through the code of DFS of S. What happens is it calls DFS of U, that terminates, so it comes back and then moves to the next neighbor. And then that next neighbor is V. So that's V. So this will be the discovery of V, which will terminate. So this is the finish of V. And then finally everything terminates, and this will be the finish of S. Right? So you see that this is for S, the standard parentheses. Square bracket is for U, and the curly braces are for V. So you see both the situations happening here. Discovery of U is discovery of U is more than the discovery of S, and that forms a parenthetical statement. If you look at these two cases, discovery of U is less than the discovery of V, but U finishes before V. The point is these intervals cannot overlap. So either the intervals are disjoint or they're contained in each other. Another way of thinking of it is if you think of this as like the lifetime, this is the lifetime of S. It's like the entire interval is like the amount of time or the interval of time that that process is alive. Then if you think about what happens in any sort of recursive setting, when you have sort of a single, it's like think of it as like a single thread running, then two processes, either their times are disjoint, so one dies and then the other one arises, or one is basically a recursive call of the other, so it's contained. Does this make sense? Questions?
Will the most inner parentheses always be like the least common ancestor?
It's not the least, it's a leaf. It's the outer one, which is the ancestor. The innermost one is like a leaf, because the innermost one, think of it as it was discovered, then it was discovered, then it terminated, because there was nothing more for it to do. So if you look at any leaf vertex in the DFS forest, that will look something like this, right? That interval does not contain any other time.
Oh no, I meant like in this case, like with U and V, S will always be like the first parentheses to encapsulate two nodes will be the ancestor, right?
Correct. Exactly. You're absolutely right. So you can think of it as the smallest interval that covers both, that contains both these intervals, is the least common ancestor. Because any interval that contains both of them is an ancestor by the claim above.
Will the same thing kind of hold if we discover U first or like V first?
Sure, then this would be swapped, right? If the DFS decided to go to V before U, then you would just swap these intervals.
No, I'm talking like not discovering S first, but like initially we discovered like V.
Okay, so actually you tell me. So suppose you start at V in this graph. What's going to happen?
Like it's going to terminate and then move to another vertex?
It's not going to terminate, right? Because so let's say you have this situation.
It's fine. It finds S.
Exactly. If you start from V, so V is going to be discovered, then it's going to find S, and then from S it's going to find V. So actually you'll have three intervals all nested within each other.
Yeah.
Right? So you have perfect nesting then.
What about in a directed case where S is pointing to U and S is pointing to V, but you start with V?
Good question. So what's going to happen is that V is going to start, then terminate. So
and what if we then go to U?
Then U is going to start and then terminate. And then finally S is going to start and then terminate. Let me draw this out. I want to keep this page for the.
So if we went back to the graph, then it doesn't always represent the least common, right? The least common ancestor then.
It doesn't represent the least common. There's no such thing as a least common ancestor in the graph, but there is a notion of the least common ancestor in the DFS forest.
Right.
Okay, so let's do this example. So you have S, U, and V, and so what did you say? You suppose DFS started at U.
Okay.
Is that the example you wanted, or you want to start at V, or what?
I think they're interchangeable.
Right.
We can start at V.
Okay, so let's start at V. Okay, so this is the DFS timeline. So I used curly braces. So this is the discovery of V, and then it's just going to terminate, right? The finish time of V. And if you look at the DFS forest, so V is just going to be by itself.
Right.
Okay, then suppose we went to U. So this has been discovered. Then you go to U. So then U is going to start and then terminate. And this is for U. And U is just going to be by itself. Then you go to S. S is going to start and terminate. And S is going to be by itself. So the DFS forest is just three isolated nodes.
Right.
On the other hand, if you started at S, then S is then actually the graph that you see is going to be the DFS tree. Because S will be an ancestor of both U and V in the way that we showed before.
Yeah, so like every time it doesn't show the exact meaning of the graph, because like by exact meaning, I say like every time the algorithm runs, the S should be the ancestor of U and V.
Why should it? No, that's not necessarily true, right? It's because I drew the graph this way that you can see that. But what I've drawn here is also a valid DFS forest.
So what is why is this meaningful if you can have multiple representations of the same graph?
It is not multiple representations of the same graph. It's multiple DFS forests within the same graph.
Okay.
So the thing is, the output of DFS is not unique. It depends on the order.
Okay, that makes sense.
Right? DFS, don't think of the output of DFS as a representation of the graph because it's a forest. So obviously it's missing a bunch of edges.
Yeah.
And so it's important to recognize that the reason that you're able to, the reason you're able to reason about this graph is because you see it drawn this way. But suppose I just gave you an adjacency list with millions of edges. How do you know what's what? And what you're saying is the ordering of DFS might reveal some information, it might not reveal information. So maybe the question, which is a very valid question, is when can the DFS or will DFS always reveal useful information?
Yeah.
And what I'm going to argue is actually it will always will for certain problems.
So in the DFS forest you've drawn, none of them have descendants.
None of them have descendants. None of them have ancestors. Indeed, the forest has no edges.
Okay.
Is there any optimizations you can make to the original function to maybe produce, I guess, more of like a meaningful one?
So good question. So the question is, can you find out the right source vertices to start from?
Right.
You could, but then that's going to require time. Now, the thing is, DFS runs in linear time. DFS is very efficient.
I can just probably think of one optimization. I'm not sure if, but so if you just always choose a vertex that has the maximum number of outgoing edges, aren't you likely to get a more meaningful forest?
You might or you might not, right? You could come up with examples where, like, for example, maybe I'm going to draw an example here where maybe this has high degree.
Yeah.
Right? But really, you would want to start from S, not from there.
All right.
So the degree is, these are very good questions. So, and I know that's why I wanted to show you these, to tell you that maybe DFS isn't producing anything, but what I'm going to show you when we do questions like topological sort is even this is going to give us useful information. Even this is going to give us useful information for processing the graph. And maybe that is what is remarkable about DFS. That instead of even trying to optimize the ordering, if you actually look at the output, there are things that you can infer even from this, like this. Even though the forest is meaningless here, one can look at the discovery and finish times and use that to infer various properties of the graph.
Professor, for this example, if you have directed graph from S to U to V, starting from S, would that be necessarily a nested one, and then the last one would be discovered would be the first one to terminate?
Say that again? No, you could still get the same situation.
So this is not nested?
No, for example, what could happen here is suppose DFS visited in this order, like it started at V, then it went to U, and then it went to S.
Okay. Okay. But
right? In this loop over here, it could have gone in the opposite order.
Okay, but if we start from S, then that's going to be the case. It's going to be
Then you have perfect nesting, right? If you started from
Okay.
S, then you'll get S as contains U, which contains V. If you started at U, then U will contain V, and then S will be separate.
I see. Okay.
Or you could have this situation here.
Okay, that's clear.
Okay?
Okay.
Good. Yeah, you wouldn't think, right, that you have to think so much about DFS, which is seemingly such a simple procedure. But when you actually get into it, it's quite non-trivial. Okay, any other questions? Okay, good. So let's go back to the statement that we had, the parentheses theorem. And what I want to do here is I want to sort of sketch out the proof. And it's not particularly, I think by now, given the kinds of questions that you're asking, I think many of you are kind of are following the arguments. But just for completeness, let me sketch out a proof of the statement. I'm to some extent cheating a bit because I am going to use this claim over here, that the vertex V is a descendant of U if and only if these conditions hold. So let's use that claim to prove this theorem. Okay, so what we'll argue here is, again, so we assume, again, so this is sort of without loss of generality, right? That the discovery of U is less than the discovery of V. Okay, so this is this picture here. So sort of rather obviously we'll say if the discovery of U, if the finish of U is less than the discovery of V, then we'll say that, well, then you're in case 2. So then 2 holds. And then let's just make an argument that neither is a descendant of the other. Now, technically, I can just invoke this theorem here. I can invoke this claim to say that neither is a descendant of the other. So you'd have to prove this, but this is not particularly hard to prove. So you've proved this statement first. And then you can apply that claim here. By claim, neither is a descendant of the other. Okay. So now we'll say, hence, assume that the finish time of U is greater than the discovery time of V. So we're assuming that the picture is like this. So what does this mean? Remember, the finish time of U is greater than the discovery time of V, which means when V is discovered or visited, DFS of U has not finished, right? Because the finish time is greater than the discovery time. So DFS of V must be a recursive call made within DFS of U. By recursive call made within, I mean it might not be made exactly in DFS of U, it might be made in a recursive call of DFS of U. Does that make sense? Right, it's a recursive call made within it, but it might not be a direct child, but a descendant recursive call, which is essentially a descendant recursive call. So DFS of V must be a recursive call made within DFS of U. So the finish time of V has to be less than the finish time of U, because it's a recursive call. And so you have this situation, and that completes the proof. Does this argument make sense? I mean, the DFS tree is basically tracking, the DFS forest is basically tracking the recursion structure, the recursive calls. You can think of it as basically looking at the recursive stack and maintaining information about that stack. Any questions about this? Okay, good. Then let me now state another useful theorem. And again, you can look this up in CLRS, and this is what I will call the unvisited path theorem. Consider the time at which U is visited. Okay, consider the time at which U is visited. If there exists a path of unvisited vertices from U to V. I mean, although technically, okay, so U has been visited, but everything else, right? So you have your graph here. U has been visited, but there is a path, again, directed path, where none of these vertices are visited. So everything except U is unvisited. Then V is a descendant. Then V is a descendant of U in the DFS forest. Does this theorem make sense? Any questions about this?
Well, why does this whole if everything except U is unvisited? Like if everything was visited, still we would be the descendant of U. If I'm correct.
No, if everything was visited, then that's not the case. Let me give you an example. Let's just take this example here. Right, so suppose this was your graph and DFS started on V. Then when DFS goes to U, there is no path of unvisited vertices from U to V.
Yeah.
V is not a descendant of U in this case, if DFS ran on V first before running on U, which it could. Remember, it's important to understand that being an ancestor or descendant might be completely well, it's not completely unrelated, but it's quite unrelated to the graph structure as you think about it.
Okay.
It's important to recognize that fact that the DFS forest might not have, like for example, you have this. It's essentially three disconnected vertices, although the graph looks like this. Because you don't know which order DFS chose when it went through that loop. I mean, again, if you think about it, you might think this is absurd, but think about actually having a graph. If you deal with a graph with a few million vertices, all you have is an adjacency list. There is no way from looking at that adjacency list, there's no obvious way of knowing where to start a traversal. And this is actually a big problem, like when you actually deal with large graphs, that you don't know where to start because all you have is an adjacency list. And so it's because, one draws the picture in a particular way that you and I can reason about it. A human mind can reason about these because the picture is drawn. But if I showed you an adjacency list that was large enough, it would be hard to reason. But that's how the computer has to reason. That's how the program has to reason.
So when we draw it out, I can see why this theorem works.
Yes.
More specifically, the picture you circled with U on the right. But if we were to do this programmatically, don't we have to keep a list of all unvisited, like the quote unquote unvisited path, and that would make our algorithm not OLEVN?
You don't need to maintain this. This is a theorem, right? I'm just stating that this is true. The proof that this is true is, again, not obvious. It requires an induction.
If you don't compute it, then how would you know with like a few million?
How would you know? Sorry, how would you know what?
If that there exists such a path without like actually computing it.
Well, actually, if you think about it, DFS is computing a path because when V is a descendant of U, it finds some path. It just doesn't find that specific path.
Right.
Indeed, graph traversals give you paths between pairs of vertices when they exist. But again, it's kind of funny. So there are situations where there is a path between the vertices, but there's no path in the forest. For example, in this case, there is a path from S to V, but if the forest looks like this, there's no path in the DFS forest. But the other thing obviously holds, right? If there's a path in the DFS forest, it's a path in the graph because the DFS forest is a subset of the edges. Again, this is talking about a path of unvisited vertices, right? So it's talking about something about the structure of DFS. There could be a path of vertices which are visited, and that doesn't imply anything about the DFS forest. Am I making sense here?
So I got confused when you mentioned that the adjacency list, like you don't know where to start, but here it's saying from you we are starting. So I'm not sure. What do you mean by where to start an adjacency list?
My point is simply that when you run DFS of G, the ordering is arbitrary.
Okay.
That's all I'm saying. I'm not saying anything more than that.
Okay. I see.
I mean, I'm just saying that many of the questions that are coming about as to, why didn't you start there or why didn't you start here? I'm just saying that starting point is obvious because I have drawn the graph in front of you. It is important that we are able to analyze DFS for arbitrary orders because we don't know what the order will be, because finding the right order may actually take more time than it takes to run DFS itself.
Oh, it makes sense. Okay, thank you.
The thing is, DFS is extremely quick, so we want to exploit that. Okay, any questions?
Yeah, I had a question.
Yeah.
Why make the distinction between unvisited vertices versus? I feel like this would hold even if it was visited, correct? If there exists a path of visited vertices.
No, I will show. This is the example that shows you that that's not the case. Actually, this example, the one example we had. Remember that if DFS went from V to U to S, then the DFS forest looks like 3 singleton vertices.
Right. So there's no. Okay. But there is actually a path.
There is a path. There exists a path, but one is not a descendant of the other.
Okay, got it.
Okay. Okay. So let me sketch out a proof of the statement, and I'm not going to do a full proof. Instead, this is going to be partial. I'm going to prove a weaker statement here. The stronger statement actually is just a straight induction on the weaker statement that I'm making. Okay, but let me make a strong let me make a simpler statement, and then we can do that. So I'll just say that if at the time U is visited, V is an unvisited out neighbor. So by neighbor, I usually mean out neighbor. Then V is a descendant of U. Okay, this is simply saying that suppose V gets visited, U gets visited, and V is a neighbor, and V has not been visited at the time U is visited, then V is going to become a descendant of U. Okay? So why is this the case? How do you know that V is going to become a descendant of U? Because when you're doing DFS, I should have called it S instead of U. You're going through the neighbors, but you might not go through this neighbor. You might go through some other neighbor first. So how do you know that V is going to become a descendant of U?
If you go through another neighbor first, it's still like a descendant.
If you actually discover V before you finish U, then obviously it's a descendant. And that, well, by not obviously, but rather it's a descendant because of this claim that we have. Right? The claim says V is a descendant of U if and only if the discovery of U is less than the discovery of V and the finish is greater than the finish of U. I want to sort of emphasize that if you use these claims, the parentheses theorem and this claim, lots of the proofs actually become fairly easy. But you need to know how to use them. So what we know at this situation is that the discovery of V is greater than the discovery of U. Right? We know that. That's because it's an unvisited neighbor of U. So we say consider the loop over out neighbors. Consider the loop over out neighbors in DFS of U. And this is by loop over out neighbors, I mean this is step 4. Right? Which is step 4. When the loop considers V, because it has to consider everything in the out neighborhood, right? So it's going for all. Okay, so I said U in neighborhood of S, but technically think of V in the neighborhood of U, right? Because U is the source vertex in this case. When the loop considers V, so either V is unvisited or it's visited. Now, if it's visited, that means that it's actually, okay, so let's do this a little carefully. So when the loop considers U, if V is still unvisited, then a recursive call to V is made. Right?
Can you please shift it?
Yeah. A recursive call to V is to DFS of V is made. So V is a descendant of U. Okay, so now what you need to do is instead suppose V was visited when the loop considers V. What does that mean? How do you now argue that it's actually a descendant?
It has to have, if it's visited, then it can't be on the stack anymore.
It can't be on the stack anymore.
So it's finished, and then the finish time is before the finish time of U, because we haven't finished U yet.
Exactly. Now you have to be a little careful. Just because it's visited doesn't mean that it well, okay, so let's be a little careful. Just because something is visited doesn't mean that it's been finished. Right? Because you have many vertices that are visited that have still not yet finished.
Sure, but the only visited vertices that haven't been finished are descendants of U.
That's right. So you've just made an extra statement, right? Right. So your observation is that the only visited vertices, well, okay, there are essentially, in some sense, there are two. The visited vertices are precisely those that are on the recursion stack. Now, when U was discovered, V was not on the stack. But when V was considered, it was on the stack. So it means that it must have entered the stack and then must have exited the stack. Does that make sense? Wait, okay.
That makes sense.
I have to be a little careful here in what I say. So, sorry. Now, let me say this: that there are three kinds of visited vertices. So, if you think about visited vertices, there are those that have actually gone onto the stack and left the stack. Those that have been, so anything that's been visited has been discovered. So either it's finished or it's not finished. And so you have to say that, okay, so let's, V was visited when the loop considers V. But V was not visited when the loop started, right? And it was not visited when the loop started because it was an unvisited out neighbor. So V was visited. So V was visited during a recursive call while, so it's visited during a recursive call while DFS or a recursive call made through another neighbor of U. Or another way of putting it is that V was visited during a recursive call. So V was visited during a recursive call while DFS S is alive. Meaning by alive, I mean started but not terminated. So if V was visited...
DFSU, should it be DFSU is alive?
I'm sorry, DFSU. You're right. U. Exactly. So V was visited during a recursive call while DFSU was alive because, it happened when you were going through that, when DFSU was going through the loop. It was not visited when the loop started, but it was visited when the loop considers U. So in that loop, it happened at some point, which means it happened while DFSU is still alive, which means that hence V is a descendant of U. Right? So this is only saying when it's a visited out neighbor. But you need to argue this when there's actually an entire path. You can do it through induction. You can do it through some kind of induction. But again, like it's not immediately obvious, but hopefully this argument the argument that I've made makes sense. Any questions about this argument? This is just a partial proof because it only talks about what happens when V is an unvisited out neighbor.
Is it okay to do this just with the parenthesis by saying like, okay, we're during execution of U, so we know that U's closing parenthesis is later on. We know that U's beginning parenthesis is earlier, and we know that V's beginning parenthesis hasn't happened yet, because it's unvisited at the start of the loop. So in order to have a valid parenthesization, V's closing parenthesis has to be first, and then that means that V is a descendant.
Yes, you can. Yes, that's probably a much cleaner argument. Yes. Yeah, I think actually, that would have been that's the better way to do it, right? You just say that you know that U started and U finished at some point, and V has to have opened at some point in here. Because if V did not open in here, then while the loop was considering, it would have actually opened it, and hence it must close in here. Yeah. Is that the argument that you were saying, or?
Yeah, that's what I was thinking.
Yeah. So you can do that, and this you can do for a visited out neighbor. You can also try to make. You need to make that argument for the path as well, right? When there's a path of unvisited vertices, and that becomes a little trickier. Then you have to do some induction. If you think about it, you can actually just apply this argument with the induction. So if you take any path, you can prove it by contradiction. So I'm just going to say this and then I'll let it be. So let's prove by contradiction. So suppose there is this path of unvisited vertices from U to V. Let's prove by contradiction. Suppose V is not a descendant. So you look at the vertex, which is the first non-descendant along the path. And so let's just say that first non-descendant was here. But that implies that the previous one was a descendant. And then you look at what happens to this edge in this argument over here, that when this vertex is visited, so I'll call this U prime, when U prime is visited, V prime must have been unvisited. Again, you sort of use similar arguments here. So therefore, then you say that, well, that means that V prime is actually a descendant of U prime, but U prime was a descendant of U. Therefore, V prime is a descendant of U. Contradiction.
Wait, how do you know that V prime is unvisited when U prime was visited? It
Say
seems
it
like
again?
how do you know that? It seems like you could have like maybe a shorter path from U to V prime, and then V prime would be visited, even though U prime.
No, what you argue is that
prime.
U prime must be visited after U.
Yeah, that's true.
Right? So what you say is, here's your timeline, right? So here is U. You know that V prime was unvisited when U started.
Sure.
And so suppose you look at the time for U prime, and you know that U prime's closing, you know that U prime's closing must lie somewhere in here. So either V prime's opening was in here somewhere, in which case you're done. And that's essentially what you argue, right? You argue that V prime must have opened somewhere in here. It couldn't have opened previously, and it must have opened in here because it's a neighbor of U prime, just by the argument that we had down here.
But there might be a faster way to get to V prime from U.
That doesn't matter.
Well, I agree it doesn't matter, but can't V prime actually get visited before U prime?
So what you're saying is, can V prime get visited before U prime? Let me see if that is. Okay, actually, you're right. So then the way that you would complete the argument is say, suppose it got visited before U prime got visited, but it must be visited after U was visited. So therefore, then V prime sits somewhere in here. And then the parentheses theorem will complete the proof for you, will complete the contradiction.
Sure.
Right, so essentially, by the parentheses argument, it's either in here or it's in here. And in either case, you're done. Any questions? All right, so I'm going to make some exercises based on these questions. I might not write down the exercises over, today or tomorrow. So what I would recommend is, I'm already pointing these out as suggested exercises for you, which is to complete the proof of the unvisited path theorem and to complete the proof of this claim here. These notes I will scan and put up. If you prove this claim, you prove the unvisited path theorem, I think your understanding will significantly kind of clarify. My plan was to I thought I'd be done with all of this in the first half an hour, and then I'd go with the main lecture topic. But clearly I hadn't planned on how much detail I would go into this. And I think this is important. I think it's actually a good use of my time that we went through the details and we went with different examples of this. Now, I do want to sort of give you maybe a bit of a teaser as to what is it that one can do with DFS if indeed one has situations of this form, where one can do DFS on a graph like SUV and just end up with disconnected vertices, isolated vertices as the DFS forest. And so the application that I want to point out, what I will talk about, and I'll complete the discussion of this in the next lecture, but let me give it to you, is the problem of topological sorting. So what is topological sort? So consider a directed graph G, and this is an important definition. G is a DAG, which is a directed acyclic graph. If G is directed and contains no cycles, right? That's what it means for G to be a DAG. So here's our problem. The simplest problem, the basic problem is given G, determine if G is a DAG. Does anyone have any good examples of where you might want to do this? One very compelling example. Why would you want to determine if a graph is a DAG? So it turns out your compiler, when you use a utility like make, it's doing this on the dependency graph of files. So consider, for example, if you have a bunch of files, right? And then there's some, include, foo.c, and it's include qwe.c or .h or whatever have you. So you have these include conditions. So what this means is, if you look at foo.c has to be compiled before this. So you can put an arrow. Typically, you would put an arrow. A dependency graph would say, well, this file depends on foo.c, so there's an arrow here. Or sometimes you can, let's say we flip the arrow, right? So this, and this is QW. So what this means is foo.c has to be compiled before this. QW.c has to be compiled before this. So in your DAG, if there is an edge UV, that means that U has to be compiled before V. And so if there is a cycle, then this code cannot be compiled. And so topological sort is finding an order of compilation. So topological sort means labeling the vertices V1, V2 up to Vn such that for all edges E is of the form Vi, Vj for I less than j, which means that all the edges are going from earlier in the ordering to later in the ordering. So what this means is you're writing out all the vertices so that all the edges go from earlier in the ordering to later in the ordering. And this is called a topological sort. This is called sorting the vertices topologically. And you can only do this in a DAG. And so topological sort is an important graph problem that comes up when you're doing graph analyses. And indeed, DFS gives you a way of topologically sorting and of determining if a graph is a DAG. I will review topological sort in the next lecture. But what I would like for you to do is to make sure that you understand all the arguments regarding the parentheses theorem, the unvisited path theorem, so on and so forth. And in the next lecture, I will review topological sort and show you how to use DFS to do topological sort and other sorting tasks involving directed graphs. So I'll end the lecture here and take any questions that you have.